Welcome to the Deep Dive. We're your shortcut to understanding the tech that's really shaping our world. Today, we're jumping into the infrastructure behind physical AI. Think robots, autonomous systems, the works. And this is actually an audio recap of a fantastic Q&A we had in our physical AI series. It's really geared towards you if you're a CTO or engineer. We're distilling insights from, well, two brilliant people in the field. First, Aditya Jami. He's CTO of Meltwater, but you might know him from his time leading big data and infrastructure at Netflix and Yahoo. Think Chaos Monkey, Priam, major stuff, and also Dr. Ashutosh Saxena, the CEO of TorqueAGI, and frankly a pioneer in robotics and AI. So our mission here is simple. Pull out the absolute key takeaways for anyone building these intelligent autonomous systems. Let's unpack this.
All right, thinking back to your Netflix days, building those incredibly resilient systems, what's like the #1 lesson for designing robust AI infrastructure now?
Yeah, absolutely. The core principles from Netflix, they map directly. You really have to embrace failure as a first-class citizen. We called it chaos as code, right? Chaos is code, right? I remember that.
Exactly. So for AI, it means deliberately breaking things, GPUs, data pipelines, model servers, just to confirm everything stays up, or at least degrades gracefully.
Okay, so testing for failure from the start. What else?
Well, beyond that, it's automating the operational headaches, creating what you might call self-healing data fabrics. Think auto-scaling for model replicas, automated patching for frameworks like TensorFlow or PyTorch, auto rollbacks if something goes wrong. Even using things like federated data meshes to automatically heal embedding stores, maybe using tools like Feast.
Feast, the feature store. Got it.
And the third piece is observable declarative infrastructure. Real-time visibility into things like data skew, prediction quality drift. You need policies to catch that drift early. Basically, treat AI like any critical service, constantly tested, watched, and fixed. It's vital for the robotics stack.
That makes total sense. Building that resilience in from day one. Now, there's this big shift, isn't there? Moving compute from the cloud right down to the edge onto the robots themselves. How do you manage orchestration in that kind of hybrid world?
Right, that's a huge challenge. It really demands a sort of hierarchical control plane. You need local autonomy, but governed by global policy. So the edge agent, maybe a robotic arm, maybe a drone, it has to make split-second decisions using its onboard models, its sensors, and then sync up with the cloud, periodically. The physical world is just too unpredictable, and latency is killer. You need that local speed.
So local decisions, global rules.
Yeah.
What about deciding what runs where?
Yeah, that leads to adaptive workload partitioning. So maybe heavy-duty stuff like neural operator inference runs right on the device using optimized chips. But bigger tasks, maybe complex planning or conversation modules, they could run in the cloud.
And what drives that split?
Real-time needs. Bandwidth constraints, battery life, latency requirements, those dictate where the compute happens moment to moment.
Interesting. So taking these ideas from massive web services and applying them to robots, what specific service design principles really carry over well?
3 really stand out for me. First, thinking in terms of event-driven microservices. Treat every sensor, camera, LiDAR, whatever, as its own independent source of events.
Right.
Use a robust message bus, something like Kafka or maybe ROS2's DDS layer for asynchronous data flow. It keeps things loosely coupled.
Okay, event-driven. What's second?
Graceful degradation and circuit breakers. Essential for the real world. If one sensor fails, the robot needs a fallback. Maybe it operates with reduced capability, but it doesn't just stop. You have to isolate faults to prevent system-wide failure.
Makes sense for safety-critical systems. And third?
Continuous integration and canary releases. Just like in software, you don't just deploy a new perception model straight onto a physical robot. You test it first, maybe in a digital twin environment. Controlled A/B testing minimizes risk.
Digital twins for CI/CD in robotics. That's cool. Now, shifting gears slightly, RoboBrain. That sounds ambitious, a Wikipedia for robots. Can you tell us a bit about how his APIs worked and what kind of infrastructure does that vision need?
Yeah, RoboBrain was about creating this huge multimodal knowledge graph linking language, vision, action data. It had 3 main API layers. First, concept discovery. You ask about a cup, it tells you related concepts, maybe graspable, contains liquid, structured knowledge. Second, embedding lookup. This gives you vector representations across different types of data vision, language, even robot joint positions, all in a shared space.
A shared understanding space.
Exactly. And third, policy synthesis. This layer could generate actual action plans, like pick up the red cup on the table. Parameterized plans that could ideally be reused by different robots for different tasks.
Wow, and the infra needed for that at scale.
Oh, serious infra. You'd need real-time graph indexing, adaptive sharding to handle the data load, edge proxies so robots could cache knowledge locally and act even if offline. The whole point is enabling that learn once, act anywhere kind of modular intelligence.
Which brings us to data. Always the elephant in the room for AI.
Yeah.
Especially physical AI, because you can't just scrape the physical world. How do synthetic data and learning by doing fit in?
They're absolutely critical. Synthetic data isn't just a replacement. It's like a continuous coprocessor alongside real-world data. You use high-fidelity simulators, think NVIDIA Isaac, Habitat Sim, to generate millions of varied scenarios. This teaches the model's general principles, environment-agnostic stuff through meta-learning. It builds those sim to real pipelines.
So sim data bootstraps the learning.
Right, but what's really unique about physical AI is that agents learn from their own actions, exploring and experimenting autonomously. A bit like AlphaGo learned Go. At TorqueAGI, our big goal is actually to slash the need for real-world data by maybe 1,000x, precisely by enabling this kind of self-supervised, generalizable learning.
1,000 times less real-world data. That's a game changer. Looking back across your career, Netflix, Stanford, is there one core principle that still really guides how you approach building these complex systems?
One principle, I'd say it's control your chaos through declarative orchestration. At Stanford, you see the raw innovation. At Netflix, you learn industrial strength reliability. This principle merges them. It means for any system, you start by defining the desired state. Then you build infrastructure that automatically figures out how to get there and stay there, even when things randomly fail. You let the system reconcile itself.
Define the goal. Let the system figure out the path. I like that. So, final thoughts. Looking ahead, what gets you most excited about generative AI's future, and how does physical AI plug into that?
Oh, I'm incredibly excited about AI shifting from just being passive tools to becoming active collaborators. You know, the next step isn't just retrieving information, it's AI that's task-grounded, context-aware, co-pilots that can call APIs, check their own work, decide the next logical step. We're really pushing that at Meltwater, moving beyond simple RAG.
Action-oriented AI.
Exactly, and that flows directly into physical AI. Imagine robots that don't just do things, but can explain why they're doing them, synthesize new plans on the fly, truly collaborate with humans in complex, messy environments. There's this convergence, right? Cloud-scale large language models, edge-optimized perception, federated learning loops all coming together. In that future, AI won't just complete our tasks, it'll complete our teams.
Complete our teams. That's a powerful thought. What an arc from resilient cloud systems all the way to these intelligent, autonomous agents interacting with the physical world. It really feels like a major convergence is happening. AI, edge computing, declarative control. So the question for you listening is, how will this potent mix redefine your next generation robotic systems?